Have you ever really stopped to think about what keeps our world running? You know, the electricity in your walls, the clean water from your tap, the products rolling off factory lines. It's not magic. It's actually this huge, mostly invisible network of specialized computers, and they're like the hidden operating system for our entire physical world. Today, we're going to pull back that curtain on these industrial control systems. So let's start with that question. What really runs all this stuff? When you flip a light switch, you just expect the light to turn on, right? But behind that simple action is this complex digital backbone that makes it all happen. And it's not like the regular IT network you have in an office. It's something way more specialized, and as you're about to see, way more unique. All right, so let's dive right in and explore this invisible infrastructure. We're going to break down what these systems are and, more importantly, how they bridge the gap between a digital command on a screen and a physical valve turning in the real world. So at its core, an industrial control system, or ICS for short, is pretty much what it sounds like. It's a computer system that controls a physical industrial process. Think of it as the master term, the big umbrella, for all the tech that automates everything from a car assembly line to the incredibly complex dance of an electrical grid. Now, you're going to hear this term a lot in the ICS world, SCADA. It stands for Supervisory Control and Data Acquisition, and this is a really widespread type of ICS that's built specifically to control things over huge distances. We're talking pipelines that cross state lines, entire railway networks, and of course, the power grid. And this image right here shows you the basic setup perfectly. Over on the left, you've got the Central Control Center. That's the brain of the operation. It sends commands out to all these remote field sites. Now, at those field sites, you have devices called PLCs or RTUs. Think of these as the hands and ears of the system. They're the ones that are actually connected to the pumps, valves, and motors. So how do they talk to them? They use what are called I/O modules. A digital module is for simple commands. It's either on or off. Open the valve, start the motor, yes or no. But the analog module is for everything in between. It takes readings from sensors that measure a continuous range of data, like the exact temperature from a thermocouple or an RTD sensor, or the precise pressure in a pipe. That sensor sends a variable signal to the analog module, which then turns that physical measurement into a digital number that the brain back at the control center can actually understand. That's the magic right there, translating the physical world into data. Now, here's where things get tricky. This very unique design, built for reliability and not for, say, surfing the web, leads to a whole different set of risks. We need to explore why you can't just secure these things the same way you protect your laptop. And that's a fair question, isn't it? I mean, we've got firewalls, antivirus software, constant security patches for our office computers. Why not just copy and paste that approach over to these critical systems? Well, the answer is because they have fundamentally different reasons for existing. And this table just lays it out so clearly. The difference is night and day. For a normal IT system, the main goal is protecting data. Confidentiality is everything. But for an ICS, the number one absolute top priority is availability, keeping the system running safely. You can't just take a power plant offline for a 10-minute security update whenever you feel like it. The system has to work. And look at the lifespan. Your laptop is old in 5 years. ICS components, they can be in the field for 15, 20 years or more. And the impact of a failure? For IT, it might be a data leak. For ICS, it could be a citywide blackout. It's a total shift in thinking, from protecting bits and bytes to protecting physical infrastructure and human lives. So you end up with this perfect storm of vulnerabilities. You've got these ancient systems running for over 15 years in some cases, often on their own weird proprietary operating systems that were designed long before anyone was thinking about cybersecurity. You can't just push out updates because every single patch needs a ton of testing, and you have to schedule downtime, which is a huge deal. And to top it all off, a lot of these crucial components are sitting out in the middle of nowhere, protected by little more than a chain link fence. So what happens when someone actually exploits these weak spots? This is where a digital problem turns into a very real, very physical mess. Let's go back to the year 2000 in Maroochy Shire, Australia. There was this guy, a disgruntled contractor, who was upset he didn't get a job with the local council. So what did he do? He used his insider knowledge, a laptop, and a radio transmitter to get remote access into the town's sewage control system. Over the next 2 months, he kept hijacking the system, overriding the controls, and forcing pumps to fail. And the result? 264,000 gallons of raw sewage were deliberately released into local parks, rivers, and even the grounds of a resort hotel. This wasn't a data breach. It was a direct environmental attack, all started with a cyber intrusion. And look, that was just an early warning shot. Years later, we saw the Stuxnet worm, which was a piece of malware so sophisticated it was designed to physically destroy nuclear centrifuges just by changing their spin speeds. And then there was the Slammer worm in 2003. It wasn't even targeting the nuclear plant, but it spread so fast that it completely clogged the plant's network, knocking out a critical safety monitoring system for nearly 5 hours. And if you think these are just a few scary stories, well, the data tells us otherwise. This chart from the US government's ICS CERT team shows a really clear and worrying trend. Just look at the period between 2010 and 2013. The blue bars, those are reported incidents, and the green bars, newly discovered vulnerabilities, they're both climbing. The threat is not only real, it's been growing. Okay, so that's the problem. It's a big one. So how do we fix it? If the old IT security playbook doesn't work, what does? The answer is to stop thinking about a single wall and start thinking about building a digital fortress. For the longest time, the main defense these systems had was that nobody really knew how they worked. It's called security by obscurity. The idea was, hey, this is so weird and proprietary, no hacker will ever figure it out. But as this quote from the National Institute of Standards and Technology makes very clear, that is just not a real strategy anymore. It's wishful thinking. The modern, and frankly the only effective approach, is called defense in depth, and the concept is actually pretty simple and brilliant. You don't rely on one single thing to protect you. Instead, you build layers of security. The castle analogy is perfect. An attacker might get across the moat, but they still have to deal with the high walls. If they get over the walls, they've still got to get through the gate. And if they get through the gate, they have to face the guards. Every layer gives you another chance to stop them. So what do these layers look like in the real world? Well, layer 1 starts with people. Good security policies, good training. Then comes physical security. Better locks and cameras for those remote sites. Layer 3 is huge, network segmentation. This means using firewalls to build digital walls between your regular business network and the critical control network. Layer 4 is actually watching the network, looking for anything suspicious. And finally, Layer 5 is knowing what to do when something bad happens anyway, having an incident response plan so you can recover quickly. So here's the bottom line. The big takeaway from all of this is that we absolutely cannot treat these systems like they're just oversized office computers. Securing the code that runs our physical world requires a completely different mindset. It demands this dedicated, multi-layered defense-in-depth strategy. And that leaves us with a really important question for the future. We're connecting everything these days: smart grids, smart cities, smart traffic lights. That means the number of ways to attack these systems is just going to explode. The challenge for all of us isn't just about building a smarter world, but figuring out how we're going to build it securely from the ground up.